Hello, am I audible?
Yes, audible.
Okay, so I see not a lot of people have joined, so I'll wait for a couple of minutes. In the meantime, I'll just share the YouTube link also. Okay, okay, let us start. So, just a second. So, I see a few people have joined, so let us start. So, till now, today will be a sort of a this week was sort of a theoretical week that deals with foundations for theoretical machine learning. As in, what do I mean by that? I mean that by this I mean that what do we till now we had some data we were using models to do what we were using models to learn we were using the data to learn different models that we had learned, say decision trees, then we had SVMs and all, we had neural networks and other things as well, but we never said what was the amount of data required. So the problem till today never had a theoretical bound on data points. So for a neural network, what is the amount of data that we require to train? For a for a very deep neural network like ResNet and all, what is the amount of data that we require? For SVM, what is the amount of data required? We never went for those bounds. Today, we'll do something like that. We'll do something called the computational learning theory, and we'll also touch upon other methods to improve performance of your model, especially used in industries like ensemble learning and other things. So these things are generally not, this should not be used in directly in research papers and all, because they sort of improve the performance without actually showing the capacity of the model. But in industries you can do it to make the model more robust. We'll come to that as well. So before we go to so let's start off with so what we call in this course PAC models, or probably accurate classifier models. So what does it mean? So till today, so the goal is to have bounds on the training data size. So I'll just a little bit, I'll give my views and insights to find out a particular bound, and then we'll do some numericals. So this has been covered in the course, so you can also go through that, but just for the sake of insight, I'll just try and give you how do you actually get these bounds. So today we want to find out what is the amount of data we require to train a model. Say we want the model to have, say, 95% accuracy. So so question we will ask is, what is the number of data points required? So this is the question we'll ask. Is the question clear to everyone? So, and what is the insight? If anyone has a doubt here, I'll just interrupt me. Otherwise, I think the question is very straightforward, because we want to have, so say we have some complicated model, so we will sort of know what is the amount of data I require. Say 10,000 data points will be good enough. So let's go to the formulation of this pack model theorem. So what does it say? So you can look to the left side of this page. So we'll see that I'll introduce a few terms like a consistent hypothesis, and that it agrees on all the data. I think you will be aware of it because you have already done the lessons for this week. So a consistent hypothesis is a hypothesis that correctly classifies all the examples in the training set. That is a consistent hypothesis. Anyways, we will define something called a delta bounded classifier. What do you mean by that? Confidence of delta, or confidence of 1 minus delta, or the error rate of delta. It means that the probability of an error, and this epsilon is the, say, I'll give you an example. Say you have n models, and for this n models, the probability of these models having an error of less than, say, 0.1. So in that case, you bound that with another probability is less than some confidence of 1 minus delta. Or to say, you can say something like that: the probability of an error being greater than some threshold for a particular model is less than delta. So what does it mean? The idea is probability of error more than a threshold is less than delta. So this is where the term probably the probably accurate classifier comes in. So this is with probability 1 minus delta, the classifier is having a bounded error, right? So if you have a doubt here, you can ask, or I'll show you how do you get the values, number of points required to get this condition of confidence level of 1 minus delta or a error level of delta. So bounded error, so you can say error is around 0.01 or 0.1, whatever you want error to be. So in case of region, this is particularly useful when you don't have concept of accuracies and all. So in that case, say you have error less than say 2 standard deviations, 1 standard deviation, and so on. So in case of a linear regression and all, so that probability is less than 1 minus delta. So you have some confidence. So you have a confidence, say, of 1 minus delta, means delta is the probability of you'll be outside the bound of error. Is that clear? Or if anyone wants some more clarification, I can.
Could you please explain the last 2 sentences?
Okay, so I'll just go somewhere below. Okay, then we'll be like, this space is cumbersome. So say, think of this thing. So your model has something called an error. Okay, error. Your model outputs some random variable. Your model, you sort of calculate the error of the model, and you say that it's a random variable. So you model the error the error of your model using a random variable, say e bar. So you say what is the probability that the error is less than some threshold, or say greater than some threshold, to show that how bad is your model. So and you say that it is delta. So what does this delta mean? So the probability of your model.
Sorry to interrupt. Are you going to consider confidence interval as a threshold here?
So confidence is the probability measure on the interval, right? The confidence, this is the confidence value. The delta 1 minus delta is the confidence value, right? So I'll give you this, the probability of a model to have error more than a threshold. Say for linear regression, this threshold can be 1 or 2. So then it's a mean square error of 2. So your error is 2. So you'll put something like this. So greater than 2 is some delta. So So in these cases, in all these cases, this is the measure of your hypothesis being bad. Is this okay now? So delta
is allowable error, na?
Yeah.
Allowable error.
Delta is the amount of error. So sort of allowable error is, I think you are a bit confused. So this we want to say that your model has the probability that is within the threshold. The threshold is the allowable error. Okay, so this is the allowable error. You're allowing this error, this threshold. So your random variable of error can have epsilon threshold, and the probability that you are exceeding the threshold is delta. Is that okay?
Yes.
Yeah, now I think it's very clear. So epsilon is the threshold or the amount of error you're allowing, and the probability that that model goes above that error is delta. That is sort of a confidence that you have on the model set of model parameters, saying that 1 minus delta times I will never go above the allowable error. So that's why it's called probably accurately correct. Probably as in for the outer probability, and accurately correct means so with allowing within the threshold. So let us derive a limit. So ma'am has had derived this. So I'll just briefly go. You can go through that. I have written it down there. You can go through that. But before we go through that, let us just have a sketch the proof of or the bound for it. So let us think. Say we will consider a consistent hypothesis. So the reason I'm going through the proof is because so that if this is a bit involved, and if in case you have an error, have some doubts, you can ask me now. Otherwise, it becomes difficult when you see the videos and you can't ask. So the consistent hypothesis, say you have k hypotheses that are bad. Say H, H1, H2, ... Hk. These are all the bad hypotheses. So these are. So what does a bad hypothesis mean? So the probability, let us consider it this way. So the probability that the error, okay, I'll just introduce. Say you have m training examples. You evaluate H on. Hi is on. So someone can tell me what is the probability that after m examples, probability after m training examples, the classifier, the bad classifier to say, was consistent. So in this case, we are considering only a binomial binary distribution. So what is the probability that was consistent? So this you can write as, since you can consider them to be the data points to be independent, data points can be considered to be independent. So what can we do? So we can productify this equation. So we can write consistent for kth example, right? This is for classifier Hi. For classifier Hi, and you can productify for I equal to 1 to k, or rather 1 to m. Is this clear, or is there a doubt here? So you are seeing that your classifier is consistent for this bad hypothesis. Say k bad hypothesis, you are choosing one bad hypothesis and saying that after m training examples, you're still finding that they are consistent. So the probability of an error here is something we bound by an epsilon that I had already told here. So we are not using this delta here, you're using this. So what is the probability that the model is making an error? So what is this? So after m training examples, your classifier is consistent means for all the m training examples, the classifier was correct, right? So what is this probability that the kth example the classifier was correct? The classifier is incorrect with probability epsilon, right? So epsilon amount of times the classifier is incorrect. That's how we have defined this threshold. So that is correct 1 minus epsilon amount of times, right? Is this okay? If you have a doubt, you ask. I think everybody has fallen quiet to this. So, and these are independent hypotheses. So for all the k hypotheses to be, for at least, sorry for that, at least one hypothesis to be consistent. So how can we bound it? So this is after training m training examples. After m training examples, one hypothesis is consistent. So we can do something like this, right? So say AI is the event that ith hypothesis is consistent. So what is the probability that at least one is consistent? That is AI union A2, A1 union A2 union A3 dot 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 AK, right? So you can bound this by the union bound, since you can take the sum of all these AKs, right? Probability of AIK from I is equal to 1 to K. So this is nothing but probability that your error for this K classifiers is greater than some epsilon. This is saying that your probability is more greater than epsilon. So the model is bad, sort of for K hypothesis. So this you can write it as K times 1 minus epsilon to the power A, which is again upper bounded by the hypothesis space size. And this, since as we had defined, will be upper bounded by delta. So this, if you use, you take the log on both sides, you get the bound that we had defined here. So what is the bound that we had defined? So you take log on both sides, you can see the calculations here, you take log on both sides and you get the bound to be m greater than 1 by epsilon, the log of the size of the hypothesis space plus log of 1 by d. If anyone has a doubt in any of the steps here, you can ask. So this is the bound. We need more examples than this. So if you want a threshold of epsilon and a confidence of delta, this is confidence and this is threshold. So it's 1 minus confidence to be exact. So if you want this to happen, so you have this particular bound for you. So how did you derive it? We derived it by seeing that each individual classifier was consistent across the m training examples you had. So with m training examples, what is the probability that you are fooled after these m? So with this we had derived this equation, and then what we did is for this k classifiers, so you have some n hypothesis space, so you have a large hypothesis space. What is the amount of data that you would require? So if the hypothesis space is very large, so the probability of getting this error would also increase. So that is the intuition, right? So you have very high hypothesis space, so this summation, this k times this would be very high. So that's why you would require m also to be very, very high. So the intuition is you can see this, right? If 1 minus epsilon, m is very high, so this goes to 0. And if h goes to infinity or very high, so you require m also to go very high to get this product to be 0, right? Is that okay? 1 minus epsilon is always less than 1, so that to the power of very large number will always tend to 0. And when you multiply hypothesis space size with it, so you when it is very large, you would also require m to be very large. Is that okay? And that is also manifested through the through this equation that we have derived just now. So yeah, Ravi, so you have a doubt?
No, sir. I was saying, yeah, you are saying correctly. The hypothesis should be very large.
Yeah, so that is the idea. So that is the intuition, and the proof is also like quite simple the way I mentioned. So you can just take the probability of an error and just compute it, and so that can be continued, and you can easily get this bound. So that we derive this bound. So there is another involved bound in case the training set is not consistent, or yeah. So in this case, we had considered consistent hypothesis. So if in case we can make error on the training set itself, so you need something to called the Hofstad's inequality. So if you are familiar with statistics and all, so you can see, this inequality. So the deviation of the expected value from the sample mean. So this is the sample mean of a random variable. This is the true mean. That is given by this upper bound. You have this inequality known as the Hofstad's inequality. So you can use this Hofstad's inequality for in place of the exactness that we had defined here. So then you can get this. So we don't have enough time to go through this proof, and it's not essential also. So we'll not go through it because we need other things to cover. So that turns out to be 1 by 2 epsilon square. Everything else remains the same. So that's the difference. So there is only two things that is different here. So you just you're dividing this by 2 epsilon square instead of by 1 epsilon. So let us solve a question. So it seems like no one has a doubt here. So this proof is appearing to be very simple for everyone. So in case you have a doubt, you can stop me now, or we'll go to solve a question now. We'll solve a question regarding this bounds and see how much we can see how to apply this. So we have this. So I'll not go before this. So sorry for that. It's some cat near the hostel. So we have this minimum number of training examples required for a consistent hypothesis and a non-consistent hypothesis with a confidence. Confidence means this is 1 minus delta, right? So confidence is given by 1 minus delta, and that is given to be 0.99. So delta is 0.01, right? So if you find any error, you can just stop. And error rate, as we had spoken, how much threshold are you imposing, is given to be 0.2. So now you're saying, what are you saying? You're saying, say y is a function given by y is equal to summation of cxi. So what is in your hand? These c's are in your hand. So there are n, say n is equal to 100. So y is of the form c1 x1 plus c2 x2 plus ... cn xn. So can anyone tell me what is the number of functions or the hypothesis space of y?
100, is it?
Be a bit careful. See, you have for each value of c, you have 4 possible c values c can take for each coefficient. So this should be ci xi, where ci belongs to the set C.
So 400.
No. So just think about it for some time. So h increase, m must decrease. I'm just writing it here so make some room for r. So for each ci there are 100, right? So how many options are there? So let's do the counting problem, right? It's a very simple counting problem. For each ci, this is also very similar to Boolean function. So you can translate this to questions that will be asked in the assignment and all. So what is this for each ci? How many options do you have?
4.
So you have 4 options. So total how many? So for each CI, so for this is for C1, this is for C2, you have 4, and so on. For C100 also you have 4. So what is the number of ways you can arrange? Since 400 or 4 to the power 100. So you can have 0, 0, 0, 0 all to the power 0, and you can have 1, 1.
Yeah, okay. Sure.
So you can have all the possible combinations, right? So you can have for each of this is the multiplication you for counting this. So if you have a doubt, somebody may have a doubt, right? Everybody, this is for each and every C you have 4 examples, and this can Y can take any combination of C with repetition. So that's nothing but M number of points in the set to the power of number of times you want to fill it. So it's 100 times 4 to the power 100. So if anyone has a doubt, feel free to interrupt. So that's it. So now you can directly calculate. So m will be greater than or equal to 1 by epsilon. This is for consistent, right? Log of the hypothesis space, that is 4 to the power 1000. This is the mod of the hypothesis space. Plus, what is the value you need? Log, what had we done? We derived just now, plus log of 1 by delta. So that's it. So you can put the values of epsilon, delta here and do the math, and you'll get 717 to be the number of training examples required to get this 0.2 error rate with a confidence of 99%. So the error rate you are allowing is 0.2, and so you see here, so it's inversely proportional. M is inversely proportional to 1 by epsilon. So you keep on decreasing the error rate. Say you want 0.01 error rate, think of that it will go like 10 times, 100 times it will go, this one will become. So it will become 70,000 examples that will be required. So similarly you can do also for non-consistent. M will be greater than 1 by 2 epsilon square, and the same thing that you have here. That also you can do the math. You get around 2000 examples because you have a square of this thing. So you need more examples in case of a non-consistent hypothesis. That's the type of hypothesis we consider. So this is actually proper bound on the number of data points that we actually need to train this classifier. So if anyone has a doubt regarding PAC models, with these were all for finite hypothesis space, finite hypothesis space size. So finite hypothesis space, if you have, so 4 to the power 100 is finite. So but if you have a say r to the power n, can you do this? So the hypothesis space is infinite, log of infinity will be infinity. So that you cannot have this bound, right? So what about infinite hypothesis space? So infinite hypothesis space, how do you find out? So for till now, for finite hypothesis spaces, when you have discrete values of your that your model can take, your weights of the model can take discrete values, that time you can have a finite hypothesis space, and you can easily use the above formulae for calculating the bounds. But what can you do in case of you don't have a finite, like in case of Rn? In case of a neural network, you will be training on Rn, so you do not know the hypothesis space is infinite, so log of infinity is infinity. So for that you would require something else, right? So if that is clear, we can go to what is called the VC dimensions. The VC dimension, yeah.
Sir, one query.
Yeah.
In the previous example, for
Yeah.
the calculation of the data required,
Yeah.
is it the minimum number of data that is required?
Yeah,
The
this is the lower bound, right?
lower bound. Okay,
Yeah,
you
you
can
can
have
use
more
more.
than that. Yeah, of course.
But it is a strong lower bound. You have calculate, if you have this much data, you will get it. That's it.
This is a wonderful technique. Looks like wonderful techniques and very useful. Looks like. The second question I have is it for one variable or is it for all the variables combined?
It is for the entire model, right? Hypothesis. We had 100 variables, right?
Oh, okay, got it.
So
Yeah,
you
for-
need, yeah.
Got it.
Go ahead.
So you are saying 100 variables means on the left side when we are inputting data, there can be 100 different labels. Is that, or like
No,
some
100 variables as in 100 weights.
100
So
weights.
hypothesis space means weights, right? So not labels. Labels are different. So for hypothesis space means different the amount of weights you are having in the network itself or in the model you have.
Okay, okay.
So here you have 100 weights, so it's and each can take 4 values, so it's have 4 to the power 100. But in case each of them took say integers, so in that case you would have n to the power 100. That would be that would have been finitely countable. So it will be infinitely countable. So you would have infinity as the hypothesis space. In that case, you would not be able to do this calculation like directly. You cannot use this mod of the hypothesis space, means cardinality of the hypothesis space. For that, you would need something called a VC dimension or the Vapnik-Chevonik's dimensions. Okay, Vapnik-Chevonik's. So sorry for the pronunciation. Chevonik's dimension. So you need.
So one more question. So
Yeah.
generally, when we start training a model, say for 100 weights, different weights, we are trying to start training it. So we do this exercise first to identify how much minimum data is required.
See, this is very theoretical stuff. So whenever you are doing that, you will ideally need to calculate the VC dimension. So for VC dimension, in that case, you'll be training a SVM or something like that. In general, practical problems, we train SVMs, we train neural networks, so they are all R to the power n. So for that, you will need the VC dimension for that space, and then you can calculate M for that. But generally, VC dimension calculation is a bit tricky. So you need, so what people do is you need to calculate, you need to do something called a hand, like you can heuristics to have say this much amount of weights, you take as much as data as you can actually. So
Okay.
this is theoretical thing. So mainly when people develop these, so these theoretical bounds are very helpful, but in case of neural networks and all, the VC dimension, you'll see calculating the VC dimension would be non-trivial. So let's go to the VC dimension. So the VC dimension, first for understanding VC dimension, so I'll define something known as the shuttering problem. So the shuttering problem means, so I've given the definition here for n given n samples, what for any labeling, does there exist a hypothesis space such that it can be shared, we can separate the points in that space. So I'll give you an example to for you to intuit. So you say you have these 3 points and you have your hypothesis space is a line. See, hypothesis space being a line means you can have infinity lines. That's why you need the VC dimension. So VC dimension, VC of h is equivalent to ln of mod h in the discrete, and this is in the continuous. So for this 3 points on a line, okay, so and your hypothesis space is a line. Can a line for any combination of plus and minuses, say consider binary for now, consider binary labels. So you'll see binary labels and multi-label are all same, because multi-labels also can be done by one versus all. So that's a side note. So binary labels would be without loss of generality in general. So hypothesis space is a line. So you can draw lines to separate positive and negative class. So can anyone tell me that can a line shatter this hypothesis space? Shatter means can any line divide the positive and the negative points always in any orientation?
The points are linearly separable, it can divide.
So in this case, is it linearly separable?
No, I don't think, because they are in the same line.
The thing is, you could like have a line doing that. So if this is the line, if this is the distribution, right? So if you have 2 positive together and 1 negative away, then you can do that. But as soon as the opposite happens, you have an alternate. Can a line exist for this?
Absolutely not.
So you cannot have a line. So the VC dimension, so not VC dimension, it cannot shatter basically. The same question, so I've just written it here. So it cannot shatter, no, for a line. So next question is, can a circle shatter this? Can a circle shatter this set of lines? For any combination, you can have positive 2 to the power 3 combinations here. So can a circle shatter it?
So with these 3 points, probably yes.
No, any point. Okay, plus minus minus. So I'll just draw circles. So can a circle shatter? You can put positive and negative in your head and try to calculate, see if you can shatter it. Shatter as in whether you can divide it into positive and negative classes.
I think yes.
Yes. So because if something, two labels are together, then you can easily form a circle like this, right? If they are not equal, so the thing you need to remember is orientation of points must remain same. And what else do you need to remember? You can only change labels, the labels. That's it. This is what you have to remember. So in this case, this is for if two same labels are adjacent to one another, you can shatter it. But in this case, can you shatter it? Minus plus minus, or plus minus minus, or minus plus minus, or plus minus minus plus. Can you do it?
No.
You can, right? This is shattered. So inside the circle is the
Positive.
positive class, and outside the circle is the negative class. So this you have to be a bit careful about. So circles can shatter 3 lines on a plane. So now the question arises, so you will not be given 3-4 line points, you'll be given n points. So what is the VC dimension? So VC dimension is defined as a subset of points that can be shattered. So defined over an instance space X of size the largest finite set of X that can be shattered by each. So it is defined as the largest finite for any configuration without a label. So what do you mean by this? The VC dimension means, so you define over an instance space X, you take a subset of that. So you have X as the instance space or the data learning set instance space. So VC dimension is this. VC dimension is this subset of, is a subset of X, a proper subset of X, such that it can be shattered by your hypothesis, VC of H to be exact, right? So for any labeling, so you have the data without a label, you assign any label, so you'll get a perfect shattering for that. So I'll give you an example to make it clear. What does it mean? So so these 2 examples will give you the intuition of what VC dimension is. So if you can shatter a VC dimension, if you can shatter a subset of X of size 6, what is the VC dimension? So if you can shatter any subset of the data of size 6, then you can shatter any, not any particular instance of a particular data, then you are done. So can anyone tell me what is the VC dimension? So the data can be 100 dimension. So there can be 100 points, but you are shattering, you're able to shatter, you know that you're able to shatter 6 of them. So what is the VC dimension? What will be VC of H? Yeah. 6. So if you can shatter a subset of X of size, so say X prime is the subset of X and size of X prime is equal to 6. So what is the VC dimension? And H can shatter it. So can you tell me what is the dimension, VC dimension of this hypothesis space for this?
5 is it?
Why 5? So what is VC dimension? What is the
Because
definition? Yeah, go ahead.
no, is it a subset of like
No, I'm
6 is
telling.
separate.
No, you have 6. 6, does x, the subset of x is 6. The size of the subset of x that can be shattered is 6. That's the size is 6. So x can
Okay.
have size equal to 100. Say x is equal to 100. And x prime is 6.
Then VC is 6.
Is it only 6? Or is greater than or equal to 6? Because you do not know whether it can shatter 7 points or less or more. You have just one statement given to you that it can shatter 6. But it has not told you that it cannot shatter 7, right?
Okay.
So you're told it can do something like this. So 6, if you can shatter 7, you can shatter 6, right? So shattering 7 is a subset of shattering of 6, right? So if you can shatter 7, you will of course be able to shatter 6. It's a subset of a shattering set. Is that okay? So it is told that you can shatter a subset of size 6. But what can you do about more than 6 size is not told to you. So what is the scientific thinking here? So more than 6 I do not know. So minimum 6 I know the lower bound, right? Is that clear? Yeah. Okay, since you're not telling anything, so let me go to the next part. Yeah, okay, let's see, it's clear. So no subset of size 8 can be shattered by a hypothesis space. What is the VC dimension? Now I expect every one of you to tell me, because this is so you cannot shatter. No subset of size 8 can be shattered by H. So what is the VC dimension?
It's 8 only, right?
No subset of
No subset.
yeah,
Size 8.
it can be shattered. So what is the dimension of VC? What is the definition of VC dimension? Defined over the instance space X, size of the largest finite subset of X.
Largest.
Yeah, largest
Okay,
finite
okay.
yeah.
So
So
is it
8,
7? Is it?
but you about 7 you're nothing is told. It's not 8. So VC dimension is not VC
Less than
dimension
8. Less than 8.
less than 8 is also considering 7. Oh yeah, less than 8. Correct. Yes. Less than equal to 7. Correct. Very nice. Very well. So it's less than equal to 7, or VC dimension is less than 8, since these are all integers. So VC is not equal to 8 means any subset of higher than 8 is will never be shattered. So anything below that 8 will be shattered. So that's, I think you have understood. So VC dimension is the largest subset that can be shattered by a hypothesis space. That's the VC dimension. So we'll do some more questions some more interesting questions. Very interesting questions. So the question is, what is the VC dimension of an ellipse in a space? So the hypothesis space is an ellipse. And the next question that arises is, what is the number of data points you require that will come to for training an ellipse? So let's see. For ellipses can be shattered for 1, 2, 3 we have seen, right? Ellipses can shatter 3 we have seen, right? Right? Hello? 3 we have seen here.
Yes, sir.
Yeah, so we have to start from 4, right? So I'll do it below. So let's do it here only, otherwise it's not done. See, so I'll give you this intuition. So this is the solution that we are doing. So VC of ellipse is greater than or equal to 3, right? This we have seen in the example before. Is everyone clear with it? because line, in case of a line, you can do it. So everyone, sort of people told yes. So let's see for 4. So remember, for VC dimension, it can be any configuration. For 4, you need not put it on a single line and tell it's not happening. So if 4 points were on a single line, positive, negative, this cannot be shattered by an ellipse. But just remember, this is a confusion I had when I studied VC dimension. So you need to select any favorable configuration of 4 points and try to shatter it. So there should not be any configuration that your model cannot shatter. In case of the VC dimension to be non-existent. Okay, is that clear? So you cannot take, you can choose any combination, but you can only change your labels. So just see this 4. Yeah, somebody had a question. Can you shatter this? Wait just a second. I'll just put this bit down. Yeah. Don't concentrate on the right. I made room. You just look here. So this is very critical for your question exams as well. So did you understand? So you can choose any configuration can be chosen. Just don't select labels. So for 4, I am choosing this configuration because it's of help to me. Say a rectangle. So can anyone tell me whether a ellipse can shatter where the vertices are the nodes or the data points? Can an ellipse shatter this square?
Yes.
Correct, right? So you have alternate. If you have something like this, ellipse can do it. Anyways, ellipse can do it. So positive. The only non-trivial case is when positive and positive are opposite sides.
In every case, it can shatter, sir.
Yes, exactly. I'm just showing the non-trivial case.
Yeah.
Other cases are trivial. You can just see. So in this case also you can shatter it by an ellipse.
Yeah.
So similarly for 5 also you can try. For 5, this is the trick that you'll use is you'll be using regular pentagons. So they are regular polygons that will help you to find out. So in endpoints whether a thing can shatter it or not. So regular polygons, since they are the most well-behaved polygons with n vertices, so use regular polygons. That is the idea. That is the trick. So always use regular polygons to come up with these. So for 5 also, can anyone tell me if it can be shattered? So say positive. So only I'm doing a non-trivial case. Negative, positive, negative. Say positive.
Yeah, we can still shatter.
Yes, we can still shatter it.
Yeah.
So maybe we can build a polygon with one side. Yes, we can still shatter this. So
But it's not ellipse, right?
No, it will be an ellipse. If you can make it, I'll show you how I.
But keeping pentagon all sides equal.
So that is not necessary, right? So I'm just telling
Okay,
you.
any irregular polygon.
That's what I told. You can take in not only polygons, anything that is of help to you to prove something.
Okay.
So that in that case you can always space out this 2 places. But once you have selected a particular polygon, you cannot change it. That you have to remember for labeling purposes. So you see it can be shattered. You can also show it geometrically, but
Yeah, that's correct. That's possible.
Yeah, it's possible. So in case of 6, let's do it for 6 now. In this case also I'll do the non-trivial case. This cannot be shattered, you will see. This you can't shatter. Because you remember a circle covers up regular or a regular pentagon. So ellipse also can do it in case of a irregular. So in this case you cannot definitely shatter all the cases. Once you have to you need these 3 points, you will also be encompassing the negative points. So VC is not 6. not 6. So it's less than 6. Is that clear? So
That's correct.
yeah.
Correct.
So VC is
Yeah.
5, right?
Right.
So VC of this ellipse is 5. That's it. So now there is a formula. I'm not going to derive it, known as a Bloomer's formula. This is beyond the scope of the syllabus. You need to derive. You need a lot of mathematics to derive it. So what does it say? You replace your original formula with log of h as VC of h. VC of h into log of 13 by, these are constants, so don't need to worry about that. So it depends upon the derivation and all. So this is the formula you need to remember. For finding out the number of points, you need to train any model with VC dimension of 5. So it's 1 by epsilon 4 log of 2 by delta into plus 4 into VC dimension of h plus into log of 13 by epsilon. So you just need to look at this formula. It's very similar. So instead of, this is analogous to log of mod h. Is this okay? Instead of log of mod h, we are using this coefficient, and this has remained the same, right? 1 by delta was still there. So it's of the same form. The only thing, as I had given you the intuition, was to use a different measure for the log of mod h. So that we have done using 8 hypothesis space log 13 by epsilon. Is that so? That's why where we'll be replacing our substituting the values that we have been given. It's epsilon delta, and you can do the maths and you can see it's also similar. It's also around 2000. So if anyone has a doubt regarding the last part, you can ask regarding the formula that I mentioned. Yeah.
So, sir, this can help you to calculate data for any number of hypotheses, right?
Hypothesis is a class, right? So it's given a neural network, it has r to the power. So you are in r to the power n. So you'll have, for n weights, you'll have n to the power r to the power n, right? Possible combinations. So if you have m parameters, so say w parameters, right? So you have, each has r to the power n options. So r to the power m to the power w will be the amount of possible parameters. So in that case, you can use, this is countably infinite, uncountably infinite. So in that case, you cannot use log of h. You have to use this thing. This is recorded, right? I've given that YouTube. You people don't get the YouTube links. You are just shared with you people on the NPTEL stuff. You can always refer to it. You have, so this is the YouTube link, and this is the Drive link where I'll be uploading the slides also. So the people on the NPTEL team also I think share it. So in this case, remember VC dimension is for a hypothesis space. So for this particular set of hypothesis space, what you do is you select a particular data point. Is that okay, Ravi?
Yes, sir. That's correct.
Yeah. So I'll do another example with you that will give you a very good idea of what is shattering. So this has been taken from a CMU EDX website. So this was there in the assignment. I'm trying to solve it. So see, so you have a set of your input is x, which is of the form of binary strings of length 4, right? So you have 0 0 0 0 all the way to 1 1 1 1. So you have 16 to the power 2 to the power 4, 16 combinations, right? If anyone has a doubt in this, yeah, 16 possible change differences.
So far, so good, sir.
Yeah. So now the thing is, please don't call me sir. So please call me Moina. And then in this case, what is actually happening is, so we will define something called a schema over x, or a classifier over x. X using 1, 0 and star, where star accepts. This is sort of a regular expression. The people who computer science people, if you are familiar with it, then it will be helpful. So star accepts both 1 and 0. So say a classifier C, or say hi, is equal to 1 0 star 1. So what can it classify? What can it accept? What does it accept? Say it is not a classifier, so something that is accepting something. So what can this accept? HI is, say, defined by this.
It can accept 1001, 1011.
Right. Accepts.
Any of the 1 or 0.
Correct. 1011. These two, right? Similarly,
Yeah.
star accepts all.
Yep. All the 16 one.
Yeah.
Yeah.
So the idea here is, what is the idea? So I'll whether you can build a class, whether this hypothesis space is able to shatter this set of strings of length 16. Can it shatter? Can anyone come up with a counterexample or a proof? It should take a couple, 1 or 2 minutes to come up with a proof of this. Can anyone think of it?
Sorry, once again, I did not get this statement. Let the class H be the set of schemas over X.
Yeah, H is the set of classifiers, right? So don't think of schema, say it's a classifier. So here this 1 0 star 1 is say
Okay.
a classifier. So it accepts these two
Okay.
strings, okay? So these two say were positive and rest were negative. Then you could have used this as a classifier, right?
Alright.
In the training data, if these two were were positive and the rest were negative, you could have used this as the classifier. But I'm telling you, for any positive and negative labels for this set of data points, can this hypothesis space shatter it? This is a very nice question. Just think about it once.
So looks like it may shatter.
It can shatter.
Yeah.
I'll give you an example, then you can, I think it will become easier. So say, let's look at this example. So do you know how to disprove a theorem? Or disprove a claim, not a theorem to be exact.
Use some data examples.
Yeah, just give a toy counter example. That's it. For proving it has to be general, but for disproving one example in the entire universe is enough. So that if a hypothesis is wrong, then it may be correct for all. But if it is wrong for one, then it's an incorrect hypothesis.
Exactly.
So that's the thing. So let's say that you had positive and negative. The positive were 1 0 1 0. So see how nicely I am just trying to form these strings. This is the idea that immediately came to me when I had this question. So whenever you have such questions, you try to disprove it first. That's the easier bet for you. So as soon as I tried to disprove, I got this answer. So you say this is a positive and rest were negative. So what was the classifier that you would need to classify this? H would have to be star, right? To
Yeah,
take,
that's right. Because every other digit is opposite, for example.
exactly. So to classify it, it has to be star. But see the counter example here, star also accepts negative, right?
Mhm.
So it cannot shatter, right? So it accepts all. So this is why I found this question very, very insightful and a very cognitively demanding example. So this is a very once you do it, it looks very nice and nicely framed. So you need to cook up this counter example where you have this alternative stuff, and then you can directly see the negative ones cannot be classified. So it's not X is not shattered by H. So that's regarding hypothesis shattering. In the next 15 to 20 minutes, as I generally extend my sessions just for your benefit, so that we can cover most of the things. So anyways, we'll do a few more things today. What we will do is we'll do something called as the ensemble learning and bagging and boosting. So this is very simple, will not take more than 15 to 20 minutes. So this was all about learning the hypothesis for the bounds for the number of training examples. If anyone has a doubt up to this, you can ask, or I'll go to this the last part of this session, and then we can wind up. So I'll give you an example, then it will become very clear. So ensemble learning will become very clear I'll introduce it with an example. So what is the people do in industry? they trained say 13, 7, 5 models, okay, say odd number of models, and make the models vote. So how do you train? Use different seeds. This is some programming terminology. So you randomly initialize weights with respect to some pseudo seed that you provide, right? So all numbers that you generate, random numbers, are all pseudo random. If you have done some computer science, so they're all pseudo random generated by algorithms, hashing algorithms. Many algorithms exist. So you give seeds and you get some set of weights that you will be initializing it. So you use different seeds to initialize and get 5 models, and then use those models to vote. So in this case it's intuitive, right? So if one model is doing wrong, so 5 models will generally not do that much wrong, right? But it does not tell you how good the model is. It may be useful for product design. Be very careful. In research, ensemble learning is not seen very well. So you can do ensemble learning, but ensemble learning as in using different modalities, that's quite different. But this is a different example where you're using the same model with different seeds and voting among them. So 3 said yes, 2 said no, so you say the output of the entire model was yes. Is that okay? Is the heuristic clear? It's just a heuristic. Yes, so let's see an example for this. So suppose you have 13 independent models predicting the outcome of a binary classification problem. Each has an accuracy of 0.8. So 8 out of the 13 predicted models, you will see in this case that how the accuracy would dramatically increase from 0.8 to 0.99. So 8 of these 13 models predicted positive class. So this is not a bad assumption that in case each of the model has 80% accuracy, each one of them can predict 88 a correct output most of the time. So 80% of 13 is around 8 by 10, so it's around 24, 111. So it's around 10. So but 8 is a good assumption. Yeah. So let's see. 8 of them said. So you have a question, Ravi?
No.
Okay, so 8 of them predicted to be positive, and said 13 out of the 13. So I'm telling you, what is the probability the model was wrong? Can anyone tell me how you would go about doing this question? Say I have the reason here on the right side, so that can give you the hint.
It is 0.2.
Exactly, like how are you doing it? So if 8 said positive, so if the ensemble model was correct or incorrect, this is given by the columns of this matrix. So if they were correct, so 8 of them were correct, right? If the ensemble model was correct, 8 of them were correct, and 5 of them were incorrect.
Right.
And now if the ensemble model was wrong, so 8 of them were incorrect, right? And 5 of them were correct. Isn't it? Is that argument clear? So if the ensemble model had to be incorrect, so the models which are classifying it to be positive had to be telling them to be negative, and the negative had to be telling them positive. Yes, so people have understood. So now we can easily model it by a binomial random variable, right? So you can
Sorry,
see,
how you are getting 8? Sorry.
oh, here, right? So for the say 5, so leave this now. So 5 said negative in the original model. So if the ensemble model was wrong, right? What does it mean? That 8 of them were. So what did the ensemble model predict? It predicted to be positive, right? The question tells that the ensemble model predicted it to be positive. So if it is predicting it to be positive, means 8 of them said positive, right? Come in. Yeah. So if this is not a correct prediction, so 8 of them must have predicted wrongly. If the output positive for a particular example is not correct, so 8 of them were wrong, right? So this will be interchanged. The positives, whoever said positive, were actually wrong.
Correct. Yes, sir.
And vice versa. Is that okay? Kamal?
Yeah, I got it. Yeah.
Yeah. So now we can easily use a binomial random variable. What will it be? So 5 of them are correct and 8 of them are incorrect. So what is the probability that the ensemble is wrong? Is also the probability of x is equal to 5, right? So x is binomial what p? NP. N is 13 and probability of being correct is 0.8, right? So what is the probability of the model was? Oh, there's a catch here. I'll come to that. So in these cases the model were incorrect, right? So I have filled it wrongly. If correct, it would have been positive would have been 8, negative would have been 5. If incorrect, positive is 5 and negative is 8, right? So 5 of them, so x is equal to 5 means 0.8, yeah, so 0.8. So 8 of them are correct. So 5 of them said correctly. Is that okay? So if I take x to be a binomial random variable of 13 and probability of being correct as 0.8, so x is equal to 5 will give me the output that the ensemble model was wrong, right? That is 13 choose 5, 0.8 to the power 5 and 0.2 to the power 8. Is that okay? So 8 of them have to be wrong, 5 of them have to be correct, and we can have 13C combinations, 13C5 combinations of that. Does anyone have a doubt here? So how am I constructing this binomial random variable here?
We need to go back and learn binomial again, sir.
So binomial means the number of times you have success.
Right.
And probability of success is 0.8. Okay. So if you have binomial is defined by this way, x is equal to 1 x1 plus x2 dot dot xn. What are xn? Or rather I'll write I1, I2, In. These are indicators. So they are, if they are correct, they'll be 1 or otherwise it will be 0. Okay. Say here 5 of them will be 1, rest will be 0. Is that okay? Or without binomial also you can do. So without binomial, but you need to know a little bit of probability to be very familiar with, like fluent in machine learning. So without binomial, how you can do? So you have a 5 positive and 8 negative, right? So 5 positive means what? 0.5 to the power, so 0.8 to the power 5. 8 of them were positive. They were correct.
Positive.
Yes, and 8 of them were incorrect. So in probability of incorrect is what? 0.2. Probability of incorrect is 0.2. And how many combinations can you form of this? 13 choose 5, right? Or 13 choose 8, whichever one. That's it. That's how a binomial is defined. So how many of them are 1? How many are 1? Say 5 are 1. So what does it mean? So you choose n choose 5, p to the power 5, 1 minus p to the power n minus 5. Now is binomial revised for people. So if it was 5 were correct, so 5 of them were 1. So any 5 you can choose and the probability you can multiply with it, right? I'm waiting. Like somebody had a doubt. Is it clear? Or say 5. So you can do something like this. What is the probability that it is 1, 1, 1, 1 and 0 others? So what is this probability? So p to the power 5, 1 minus p to the power 5, 8, right? So we have 13 of them. So you have output of this string will have this probability, right? So 5 probability of 1 is p, probability of 0 is 1 minus p. So this is the probability of this string. But you do not care where the 1 is. So how many ways can you interchange 1s? So you can interchange it as 13 factorial, and once there are 5 factorial into 8 factorial. So I just derived the binomial again.
Correct, sir.
Yeah. So you're dividing by 5 and 8 factorial because you have 5 ones, and interchanging between them does not make any sense in the permutation sense. Anyways, so I'll give you a side note. So why is this helpful? So this is helpful because this keeps the bias same and reduces the variance. Okay. So how does it reduce the variance? You will remember that the variance is if you are taking the this is known as the sample mean, reduces as variance of each of this random variable by m. So if you have a large number of samples, variance becomes what? It becomes 0. Variance tends to 0 if m tends to infinity. So if you have very large, this is the law of large numbers. So you will be getting the actual mean of the distribution. You will not get any distribution, you will get the actual mean if you take very large number of samples. You toss the coin 10,000 number of times and you will see that you will get 0.5 only as the probability of a head if the coin is not biased. Okay, this is because this m is becoming very large and variance becomes very small. So let's prove this. So this is used many times in the course in this week, so I'll just try to give this side note. So in case you did not understand, so what is the variance? Variance is defined as expected value of the difference between the mean and the random variable, right? This is very important for your example and all, because this is what variance is used throughout. So this is the variance. So I just substitute value of y here and subtract this. Say I call this mu. So this is expected value of 1 by m. Say rather I'll just take m outside, taking it to be a 1 by m square. I'll take the LCM xi minus mu square. Is this clear how I am doing it, or is this not clear? So I'm just multiplying m here, so you have m mu and you are taking 1 mu with each xi. Is it okay?
Yes.
So now I'll substitute, I'll just you know this, right? x1 plus x2 dot 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 xn whole square, what is it? Summation of xi square plus summation of xi xj, I not equal to j, right? So you need to take product of any two. That's it, right? You will multiply, this means x1 dot 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 x2 xn into x1 x2 dot 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 xn. So you need to multiply this with this and so on. Are you seeing why is this the formula? This will be multiplied with this will be multiplied with this and so on. So xi and xj, for all combination I is not equal to j, and for if I equal to j, I xi square. That's it.
Correct.
So I'm just expanding it. So this is expected value of xi minus mu whole square. So I'll put the summation I is equal to 1 to m xi minus mu whole square plus summation I not equal to j xi minus mu and xj minus mu.
Correct.
So now you can use linearity of expectation. You can separate the sign. We know that expectation of a plus b is expectation of a plus expectation of b. So this turns out to be 1 by m square summation of I is equal to 1 to m. So I'll just write it here for the sake of clarity. 1 by m square summation of expectation of xi minus mu square. Remember, these were IID, means identical and independent, plus 1 by m square summation of I is equal to 1 to m, I not equal to j to be exact, expected value of xi minus mu xj minus mu. What is this? Expected value of xi minus mu is the variance of x, right? So you have m of them. and this is 0. I'll show you why. Is this first term clear? Why is it 1 by m square into m variance of this?
Yes, sir, you told earlier also.
Yeah. So this is clear. So this is the variance of x. So, and the second term, expected value of xi, x and y. What is it? Is it expected value of x comma y, right? If x and y are independent. So you can factorize x and y if they are independent. So you clearly see f of x minus mu, x1 minus mu, x2 minus mu is nothing but expected value of x1 minus mu into expected value of x2 minus mu. What is it? It is 0, right? Expected value of x2 is mu, and mu minus mu is 0. Did you see why is the second term becoming 0? This is also known as the covariance. The covariance of xi, xj is 0. Since they are independent, that's it. I hope that's clear. So the variance reduces as you increase the number of samples. So last thing for today is the bagging and boosting algorithm, or the AdaBoost algorithm that we will be doing. It's very interesting. So what would you do if the data set is very large? You could do something like split the data set deterministically and train M models and make them vote, right? This is known as bagging. You generate S n random bags and train n models.
The bags or batches.
Yeah, whatever. And train n different models and make them vote. So this is known as bagging. But bagging is not a very efficient algorithm. Why? What is the drawback? Not good for small data sets. So if you have a small data set and train on a further 100, divide into 100 subsets, you will even have lesser data, right? This is very important. I'll write it very clearly. Not good for small data sets. So what you can do is you can randomly sample S1 to Sn with replacement. That you can do. But in that case, there is a possibility of a bias towards things that were sampled again and again, right? So the AdaBoost algorithm is a mixture of these two. So you want to sample. So I'll give you the example, then it will become very clear. But before that, I have the algorithm written. I have the entire idea very clearly written here. So I thought of how to introduce it. So this is the best way. Trying to make bagging better. What is this? Deterministic bagging or random sampling does not change over time. Say you are making error on this data set. You're making error here. So ideally you should sample this more, right? More for the model to learn, so that you do not have a bias sort of a thing. So the AdaBoost algorithm sort of does this. What it does is, whenever your model is making any error on a particular points, so you have these points. So the AdaBoost algorithm or the boosting algorithm, any boosting algorithm, what it will do is increase the probability of sampling. If this intuition clear, if it is not clear, then the entire algorithm will not be clear. The algorithm is very simple. The intuition is the thing.
So Monik, suppose I have say 10,000 sample records. Okay.
Yeah.
And I need only say 700 in the previous example that we take, for example. Minimum requirement is 700 and I have 10,000.
Yeah.
So what I will do is I will create badges of 1,000.
That you can do, but you generally do not know what is the size. So in a neural network, it's very difficult to calculate the VC dimensions.
I'm just trying to say, put it in a layman's term.
Yeah.
So I create 10 badges of 10,000. Oh, sorry, 1,000 each, right?
Yeah, 1,000.
Will I go and train 10 different models?
Yeah, you'll train in a naive bagging algorithm. You'll train n different models and then make them vote.
Then make them vote. Okay.
Yeah.
I am training 10 different one, and out of that, one of them is giving error. So I increase the sample size from 1,000 to 1,200 for that particular model.
That's the difference. Like if you have a small amount of data, so when you're getting error for a particular model in a particular say iteration, say you are not training the n models together, right? You will train ith model at a particular ith time. So in the ith time, if you have random sampling, you are seeing the ith model random sampling. I'm not talking about deterministic, cross deterministic for now. Random sampling. So you're seeing in random sampling, this bagging algorithm is we are throwing it away before only because it is decreasing the number of data points. So let's say we are randomly sampling and bagging. In that case, what is happening? Let us consider. Okay.
Okay.
So in that case, you will see that HI is doing badly on this data set, on this data points badly. So what would you ideally like? You would like HI plus 1 to not be sampled like uniformly. You would like, I think this question is very pertinent and everyone will be very clear after this. So you will want HI plus 1 to pay more attention to A. Is that okay? So you would want the next model to pay more attention to the sample that you were having wrongly classified.
Correct.
That so this you in the random sampling that is not possible. So you come up with a boosting idea where you change the distribution through which you sample. You sample through a multinomial distribution. So what is a multinomial distribution? If you have n things, so 0.1, 0.3, so that 0.2, so that the summation of pi is equal to 1, from I equal to 1 to n. So if you have n 1 to m, say m points, so each one have a probability of pi being sampled from being sampled. Okay, so if you have say n times, say 1000 times if you run, so this will be sampled 10 times. So this is the idea, sort of a thing. Not 10, yeah, 10 times, yeah, or 100 times, yeah. So this is a multinomial distribution. Each of the data points, each of this have a particular probability of being sampled at a particular time, independently of the others. Independent of the others is wrong, but independently of the next pickup. So when you sample the next time, that also will be independently sampled based on the same distribution, a multinomial of D. Is the multinomial distribution clear? So if you have say 4 points and each, or 3 points, say 0.3, 0.4 and 0.3. So 30% of the times this will be sampled, 40% of the times this will be sampled, and 30% of the times this will be sampled. That's it. That's how multinomial is. So in the subsequent steps, you will do it independently. That's the thing. But in the particular step, it's not. Each of them are not independent. Sorry for that, because they're totally dependent. One is sampled, others will not be sampled. Totally dependent. So let's see. So the idea is you take a particular D1, you sample a data set according to DT, train a model, see where the error was made, update DT to DT plus 1 and do it continuously, right? Is the idea clear? So wherever you're making a mistake, accordingly you update the distribution through which you sample. That's the AdaBoost algorithm. So how do you do that? Very nicely intuited the algorithm. This is the very nice. So you say you have this data points.
Manik, one more question.
Yeah.
So if I'm going from D to DT plus 1,
Yeah.
would there be a case that error increases instead of decreasing?
Yeah, it can happen. So again, you will do DT plus 2 and so on. But you will be training eventually many models, and then that will actually cancel the noise and all.
Okay.
That can always happen. So say your hypothesis was very good, and those points were outliers, and you concentrated more and more on them, so the model will become bad. And again the next model. And remember, all these models will be trained from scratch. They're not like other models. They'll not be continued. They'll be trained from scratch. So did you get it? Why I'm telling you they can decrease?
Yeah, I got your point.
Yeah, so the algorithm is there are m examples, and we'll start off with equal probability. Okay, start off with equal probability and sample a dataset ST. Is that okay? Sample ST. Sample ST, train a hypothesis HT and store it. Store HT. Now you see, you calculate the probability of an error, or the expected value of an error, not a probability. Expected value of an error, that is nothing but this, right? Expected value is of a function of a random variable is given by summation of x f of x, right? Or probability of x f of x. This is the expectation of anything. So the epsilon t is the expectation of an error under the sampling distribution. Is that okay? So this under the sampling distribution, you're making an error that is given by this indicator. What does this indicator signify? When they are not equal, ht of xi is not equal to yi, means error is made. In those cases, it will be 1. Rest, it will be 0. So, and you will be taking the weighted average of the probability of sampling. So that is given by epsilon t. That is the expected value of a error. Now, tell me something. If your expected value of an error is very high, so what would you like to have for a, say, a scaling factor? So the scaling factor epsilon alpha t will be inverse of this. So if your error is very high, so you would want epsilon t to be
Small.
just one second. So I'll come to that. It will be, we want it to be low because I'll show you why. This is the desire. I'll come to it, why it's required. This is the idea. So if error is low, I want epsilon t to be low. So you can see if error was low, so 1 by error was high, right? No, sorry, very sorry. So error was, I'll come to this. If error was low, model is good, right?
Correct.
So model is good. So alpha t is a measure of how good is the model. Alpha t measures how good is the model. So alpha t will measure how good is the model. So 1 by epsilon will be very high for a model error that is low. So log of 1 minus epsilon will also be very high. Log is an increasing function. So why do I require this alpha? I'll come to that. So in the meantime, how will I update the distribution dt? So I'll update it somewhere, something like this. So it is exponential of alpha t into the product of yi ht of xi. Why I'm taking product? See, if you both of them are equal, then it is 1, right? So I'm taking ht to output plus 1 and minus 1. So if they are same, minus 1 is 1, plus 1 is 1, right?
Yeah.
Yeah. So what will happen to the alpha? E to the power minus alpha plus into some positive number, right? So this is e to the power some negative number, right?
Correct.
So dt plus 1 is becoming small, right? So its negative number means 1 by epsilon is very high. So you're dividing by a large number, so dt plus 1 is becoming small. Is that okay? So dt plus 1 is becoming small means for correct samples, you are not giving that much importance in the next round compared to the incorrect samples. If it is incorrect sample, this would be negative and this would become positive, as you would see, and dt plus 1 would increase. Is the idea okay? So if they were opposite, so this product is minus 1, right? So my plus 1 minus 1, the product of these two is minus 1. So in that case, minus 1 into my, so I think people have problem in this. So yi ht of xi, for wrong, what is the output? It's minus 1, right? So if this is plus 1, this will be minus 1. If this is minus 1, this will be plus 1 in case of a wrong classification, right? And in that case, this exponent will be positive. And if an exponent is positive, what happens? dt to the power exponent positive will make it large, right? The probability of the functions that were making an error would become very large, right? And alpha t will scale it if a model is doing very well, so it will have a larger weight on this negative sample. I think there's some issue, right? Is that okay? So the idea is I want the next subsequent sampling to happen such a way that then incorrect samples were sampled more, incorrect data points. So that's what is being captured by this exponentiation, right? And then finally, since no one is asking, finally you will have the total classifier. As I told you, alpha t being high means a good classifier. So here you will take the weighted sum of ht with alpha t. So alpha t for a high alpha t, you will have you will have more importance. So alpha t being high means the classifier is good, you will give more importance to the classifier. Ravi was asking me why can a model become bad. So I'm telling him, see, in this case the algorithm itself will pay attention to the models which are good, right?
It should.
Yeah, because alpha t is capturing good classifiers. The more alpha t is, the better the classifier is that is being captured. And we are also taking care of the fact that the distribution that you are sampling from is scaling accordingly. It was bad for this. So bad for this, the probability will increase for those and decrease for this and increase for this. So that is being taken care by this function. So I'll do an example to make it very clear. So just the algorithm stating is not very helpful. So say you have these 5 data points, 1 to 5, where this is the true and this is the false. This is the output. So you can see after hypothesis 1 is being trained, this is the say output. So you for sample 1, 2 and 5 you are correct. For 3 and 4 you are wrong. Okay. So can anyone tell me what is the value of D1? D1 will be 0.2, right? That will be initialized 1 by 5. Initially, that will be starting off with this initialization of equal sampling. We'll be using D equal to 1 by 5 for all I to sample the first set of distributions, right? That is this D1.
Everybody has 20% probability.
Exactly, that's the correct idea. And after the first model is being sampled, so what will we do? So since this is 20%, I can take 1 by 5 out and 1 plus 5. So in how many cases this is telling me in how many cases the model was incorrect, right?
2 cases.
So, yeah, 2 by
cases.
5. So remember, you evaluate the model on all the training data, not on just the data you are sampling from. You may have not even taken 2 and 3 in your when you're training, but you will be evaluating it on all of them. That is to take into account. So this will give you epsilon 1. What will become alpha 1? That will be 1 by alpha log of 5 by 2 minus 1, that is 3 by 2. So half log 3 by 2, right? So this I have calculated previously also. So now, so remember that it's since the distribution come to it also. So now you tell me which are the negative samples. So that D2 of 1 will become proportional to D1 of 1. That is nothing but half times e to the power. Is it correctly sampled for the first example?
For first example, yes.
Correct. So it is correct. So what will be this product? This will be plus 1, right? 1 into 1 is 1. So this is minus log half log of 3 by 2, right?
Okay.
Into y1 is also 1. H1 of x1 is also 1. So the product is 1, right?
Yep.
So now you see you are actually decreasing the weight of D2 from half. You are actually multiplying it by, so it's minus half. So half to the power 2 by 3 half. That is less than half, right? I'm taking this to the exponent and exponent of log is cancelled. So there's simple logarithmic calculation. Similarly, this will be true for all the positive ones.
Right. For
D2
D2 also, for D5 also.
D2 will also, correct. D2 will also be this. D5 will also be this. And D2 of 3 equal to D2 of 4 will be equal to half e to the power minus log of 3 by 2 to the power half into minus 1, right?
Yeah.
Because they're wrong.
Yeah.
So this will turn out to be proportional to 1 by 2, 3 by 2 to the power half. So now, since it is a distribution, you will sum di, that is nothing but half, 3 into 2 to 2 by 3. This is known as Zi, Z2,
Plus
plus 2 times 3 by 2 to the power half. And you will divide each of them by this to make the sum equal to 1. That's all. There's no rocket science here. So you will divide each di by this Zi, Z1, okay? To get the distribution. That's it. And now it is saying, say you had only one hypothesis. So what would be the output? So in that case, what will be the output? It will be sine of alpha, that is, say for example, h of x1 is alpha of 2. So is it alpha of 2? No, alpha of 1 into h1 of x1. So what is h1 of x1? h1 of x1 is 1, right? And alpha is half 2 by 3 to the power 1 by 2 by 1 by zt. So this is the sign, and it is clearly greater than 0. So you output 1. So if you have more, in the next example, say the model was very bad and it classified it as negative. In that case, this alpha value will be this will become negative, but this alpha will be very small, and you still would output 1. This is why the AdaBoost algorithm tremendously increases the performance. Is that okay?
yes, sir.
So this is a very nice algorithm people use for product design and all. So I hope this was insightful. If anyone has a question, you can ask, or I will end the session for today.
Certainly insightful, Manik.
Thank you.
Thank you, Anik.
Good to-
Thanks
good
a
to
lot.
hear that it was helpful. Thank you. So we'll meet next week again.
Sure,
Okay,
Manik.
bye.
Sure.
Yeah.
Nice. Thank you so much for your time.
Yeah. Thank you.